this video, we will be looking at how to determine chemical formulas given a chemical name. And so really the best way to do this is just to start looking at examples of names and kind of decoding what it is that they mean. So let's start by looking at an example. Example number 1. Magnesium phosphide. Magnesium phosphide. And so it's first important to figure out what kind of compound we have here, whether it's going to be an ionic compound or a covalent compound. And the way you know that something is an ionic compound the quickest is just by determining whether or not it contains a metal. So magnesium here, if we look at our periodic table, we can note that magnesium is a main group metal. So this is going to be an ionic compound. So I'm going to write down this is ionic. Ionic. Let me spell that correctly. Ionic. And next, I need to determine what this second part of the word is. Well, this IDE on the end indicates to me that this phosphide part means that it's an element. The other option would be that it would be a polyatomic ion, but if we have an "ide" ending, IDE, at the end of a word, the suffix, that means that we have an element. If we look at another example real quick, so let's say magnesium phosphate, we still have an ionic compound here because we have magnesium, which is a metal, but then instead of ending in "ide", this ends in "ate", which indicates to us that it's a polyatomic ion. The other ending that would indicate that it's a polyatomic ion is "ite". ITE also indicates a polyatomic ion. So let's figure out the chemical formulas for these two examples here. For any ionic substance, we use a method called the crisscross method. Crisscross method in order to determine I can't spell today, crisscross method in order to determine our chemical formulas. And in the crisscross method, we start out by writing the two ion forms of the elements or the polyatomic ions that we have, and then we cross the charges down in order to get a balanced chemical formula that has a neutral charge. Because when we get a chemical formula, the whole point of chemical bonding is for things to become more stable. And things are more stable if they steal electrons from each other and then they form a bond together. If we have a positive and negative charge near each other, it's going to take a lot of energy for them to remain apart from one another. So they'd rather attract towards one another and form a bond. So let's start by doing this crisscross method. So we have magnesium, and we have phosphide, which we said is going to be the element phosphorus. Okay, and then we just need to look at our periodic table and determine what the charges of these ions will be. And so we learned before that this first column has a +1 charge, and then this next column has a +2 charge, and then a +3 charge here in group 13. And then if we start over in group 17, we have a -1 charge, then a -2 charge, then a -3 charge. Remember also that group 14 doesn't generally form ionic bonds. Generally, those elements form covalent bonds. So magnesium is in group 2, so it's going to have a +2 charge, its ion form. And then phosphorus is over here in group 15, so it's going to have a -3 charge. Then the crisscross method makes it super easy to make a balanced chemical formula. All we do is we rewrite the chemical symbol, we take the charge from the opposite element, and we bring it down as the subscript. So this 3 up here, we're just going to take the absolute value of the charge, not the negative part, but just the 3. We're going to bring the 3 down here to say that we need 3 magnesiums. And then for phosphorus, we're going to do the same thing. We're going to take this 2, bring it down as a subscript, and put that there. And let's talk a little bit about why this works. Well, we need our charges to be balanced. So in order to do this, we need to end up with basically the least common denominator. So if we have an Mg that has a +2 charge and a phosphorus that has a -3 charge, that's obviously not balanced yet. So then we're going to add another one. Let's say +2, -3. So now we have -6 over here and +4 over here. So now it becomes clear to me that all we need to do is add one more +2 charge to get a balanced charge. Now we have +6 and -6. And that is 3 magnesiums with a +2 charge and 2 phosphoruses with a -3 charge. But instead of drawing this picture every time and working this out, notice that it comes out the same if I just take the charge on phosphorus, bring it down as a subscript for magnesium. That gives me 3 magnesiums. And then take the charge on magnesium and bring it down as the subscript on phosphorus, which gives me 2 phosphoruses. So this is just a quick and easy way of doing it instead of having to think through balancing charge every single time. So let's do this for a polyatomic ion. So once again, we have magnesium, Mg, with a +2 charge, and then we have the phosphate ion, which you do need to memorize the most common polyatomic ions, which you have a list of. But for now, you can reference your list. Notice phosphate is PO4 with a -3 charge, meaning that this PO4, the whole thing, has a -3 charge all together. So then when we do our crisscross method, we're going to end up with 2 phosphates in our final chemical formula. So we want to make sure we leave the parentheses around phosphates. We know there's 2 PO4s, which I'm going to draw you a little picture. It's 2 of the whole thing in our formula. That's a super important idea here, because otherwise we're going to end up with a very confusing formula that doesn't make sense. It's 2 complete PO4 ions coming in here. So we have Mg, do our crisscross, or bring down this 3 magnesiums, and then we're going to need 2 phosphates. So I'm going to go ahead, put parentheses around my phosphate, and the 2 is actually going to go outside the parentheses. PO4, and we have 2 PO4s. So we have 2 PO4s, and then we have 3 Mg plus 2s, or 2 pluses. G plus 2. We have 3 of those, which I know I keep going off the screen here. So let me adjust that real quick so you can see a little better. Mg plus 2. All right, so the next example that we are going to look at is a substance that is not a main group metal. So if we have an ionic substance, like let's say copper, 2 phosphate, or let's do phosphide first. Phosphide. We have copper 2 phosphide. When we look at the periodic table to try to determine our charge on copper, Cu, you might notice that it is in the transition metal. So we can't determine the charge from the periodic table. So instead, for transition metals, we give the charge as a Roman numeral written in parentheses. So this Roman numeral 2 tells us that this copper has a +2 charge, or oxidation state. So It's really easy to know the charge here. It's already written down. So copper has a +2 charge. And then phosphide, that I indicating to us that this is an element. That I tells us it's an element phosphorus, which if we look back at our periodic table, remember it has a -3 charge, the phosphide ion. So now we just do our crisscross. Copper, this 3 comes down and becomes the subscript on copper, telling us that there are 3 copper atoms. And this 2 comes down, telling us that there are 2 phosphorus atoms. So our chemical formula is Cu3P2. Next up, example number 4, let's do something that is not an ionic substance. Let's do an acid. So acids are a little bit tricky because they have their own special group of naming rules. So I'm going to give you 2 examples here. The first one is hydrosulfuric acid. And then the second example, which I'm going to put over here next to it, example number 5, is sulfuric acid. Sulfuric acid. So it's very easy to know when you have an acid because it has acid in the name. So that's super easy to note. The tricky part is knowing what is bonded to the hydrogen. So acids always are going to start with hydrogen as the first element. Hydrogen. And hydrogen, if we look at our periodic table, it's over here in group 1, so it has a +1 oxidation state, a +1 charge. The tricky part is knowing what is bonded with the hydrogen. So we have some weird acid naming rules that go with this. So this hydro prefix, right here, tells us that the thing bonded to our hydrogen is going to be an element. And then over here, we don't have that hydro prefix, so if we have no prefix, then the thing bonded to our hydrogen is going to be a polyatomic ion. A polyatomic ion. So, over here we have hydrosulfuric acid. Notice that we changed the ending to ic as well. You should be able to tell now that the element we're talking about is sulfur. We just changed the ending to ic. So I'm going to put sulfur as my element bonded to my hydrogen. And then come over to my periodic table and notice that it is in group 16, meaning it has a -2 oxidation state. Sulfur's here, group 16, -2 oxidation state. And then, once I have this information, all that's left is to do my crisscross. So hydrogen, this 2 is going to come down and be the subscript on hydrogen. So we have 2 hydrogens. And then this 1 is going to come down, and we have 1 sulfur. But when we have a chemical formula, we don't show a 1. We don't show this 1. Because it is implied that it's there. So instead of writing H2S1, we're just going to write our formula as H2S. And if there's no subscript, it is assumed that there is only 1 of that element. So this would be our correct chemical formula. Then coming over here to sulfuric acid with no prefix, that means that we have a polyatomic ion bonded to our hydrogen. Now, there are 2 options for what the polyatomic ion could be. We have 2 polyatomics, sulfate and sulfite, that have sulfur in them and kind of sound like they could go here. And the way that you will know this is by the way the ending is in the acid name. So if you have an ending ic, that means that it was the polyatomic ion that ends in 8 that we started with. So here we have the ending ic, so it means that it's the polyatomic ending in 8, so that would be sulfate, SO4 2-. If instead this said us, OUS, as the ending, sulfurous acid, that would mean we started with the polyatomic ion that ended in ite, which would be the sulfite ion. So you kind of have to look at those endings to determine which polyatomic ion is in your acid. So here we said it's the sulfate ion because we have ic. So ic means we started with the 8th ion, so sulfate, SO4 2 minus, SO4, I'll put in parentheses, 2 minus, and so now we just do our crisscross. So this 2, we're going to have 2 hydrogens, that comes down, 2 hydrogens, and then we're just going to have 1 SO4. So SO4, and we're just going to have 1 of those. But we really don't need this one here. And if we don't need anything outside the parentheses, we actually don't need the parentheses either. So we're going to shorten this. We're going to get rid of that one. We're going to do H2SO4. And we don't need those parentheses because we know there's only one SO4 here. So this would be our correct version of that chemical formula. The last class of compounds that we need to talk about determining formulas for is covalent compounds. And with covalent compounds, we have this series of covalent of prefixes that we put on the words. Prefixes, fixes, that we put on our names. Because with covalent compounds, we have 2 nonmetals. And so these nonmetals aren't bonding by stealing electrons from one another and then having 2 oppositely charged ions that attract. Instead, they are bonding by sharing electrons. And so there's no charges involved with covalent bonding, so we need a different naming system for determining how many of each nonmetal we have. And so we do that with these prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And so each prefix indicates a different number of atoms. So in this first example, we have trinitrogen pentoxide. And this tri means 3. So that means that we have 3 of the nitrogen. And then this pent means that we have 5. So we have 5 of the oxygen or oxide. Remember that IDE indicates that this is an element. So covalent formulas are perhaps the easiest ones to write because there's no crisscrossing. All you have to do is look at the prefix to figure out how many you have. So now I know that I have 3 nitrogens, so N3, and then I have 5 oxygens, O5. Trinitrogen pentoxide. Easy. The only tricky part to this is when you only have one of the first elements in your covalent formula. So at the beginning, notice this just says nitrogen. There's no mono at the beginning. And then we have monooxide as the second part of our formula. You only put the prefix mono on the second element in your covalent formula, or in your covalent name, not on the first one listed. So even though there's no prefix here, we know that there is 1 nitrogen, and then there is a prefix here, mono, and we know that there is also 1 oxygen. So 1 nitrogen, 1 oxygen, NO. No. Kind of funny. So it's pretty simple and straightforward for covalent compounds and determining their formulas. You just have to remember that if there is no prefix on the first word, then that means there is one of that